You're listening to EE Times on Air, and this is EE Times Current. I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Dr. Charlotte Frenkel from Delft University of Technology explains why she thinks it's important to embrace digital as part of the neuromorphic design process. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of the Czech Technical University in Prague.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny is talking neuromorphic chip design with Dr. Charlotte Frenkel, an assistant professor in the microelectronics department at Delft University of Technology in the Netherlands. After the interview, we will be talking to Ralph Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Charlotte has made a major impact in a short time. During her Ph.D., she created a tiny digital neuromorphic chip that bested previous efficiency records. She went on to win her university and national thesis prizes in 2020 and has since won many other awards. Charlotte has contributed significantly to the community by open sourcing her designs and through her work on the NeuroBench project intended to create meaningful benchmarks for neuromorphic and other technologies. Though she's a digital designer, Charlotte advocates for a pragmatic approach to building neuromorphic systems, focusing on the best technology to achieve a required function. There are links to her work and some of the specific papers we'll be discussing on our website. You can check them out at brainsandmachines.net. I interviewed Charlotte online. Charlotte Frenkel, welcome to Brains and Machines.
Hello, happy to be here.
Let's start with the usual question. What is your technical background and how did you get involved with neuromorphic engineering?
So my background is in electrical engineering. So I'm a hardware designer at heart. And somewhere in my master thesis, my curiosity got trapped by trying to make things more brain-inspired. So this was really out of pure curiosity, and now I'm pursuing this field by passion.
I think it's good that we jump straight into hardware design and digital design because while you were doing your PhD, you developed a chip called Odin, which has 256 neurons on a tenth of a square millimeter of silicon with an energy per synaptic operation going down to 12.7 picojoules, I believe. Can you tell us about that chip and the insights that you wanted to build into it? What was your kind of thought process going into that design?
So the core idea at the beginning of my PhD was to try to make things digital. Because digital is well known, is scalable, is easy to design, so you can get your proof of concept quickly, as opposed to mixed signal, where there's a lot more effort involved in the design. So at the time, the IBM large-scale chip True North was barely out. Loihi was not out yet. So it was still, I would say, quite early on in the development of digital neuromorphic chips. And I was just trying to make things a bit more efficient by just simplifying the design. So the goal of Odin was to make things as simple as possible while keeping some versatility in neuron and synapse behaviors. And I would say that the outcome of Odin is twofold. First, I have learned how to build things efficiently. So it's really a learn by doing approach, a pure bottom-up process driven by insight from neuroscience. And the second outcome is that I have had such a pain making this chip work, benchmarking-wise. So the chip was fully functional as intended, but when it comes to extracting more than 90% on MNIST, it was such a big pain. And at that point, I realized that I perhaps need to have some more top-down insight with machine learning in order to make those chips work. But it's really with Odin that I understood how to make things efficient.
So in 2023, you wrote a comprehensive paper covering bottom-up and top-down approaches to neuromorphic engineering. It's a great paper, I have to say, and I wish something like that had existed a long time ago. But can you start by explaining how it came about? And I'm assuming, I was going to get to benchmarking later, I'm assuming part of the inspiration came from this benchmarking pain you talked about earlier.
So as a young PhD student, I was trying to have a nice comparison table where you add your column to say, oh, look, my chip is that many % better than the state of the art. So when I wrote the Odin paper, it was perhaps in 2018, I think the preprint came out. And I just realized making this table was such a pain because just defining the picojoules per synaptic operation. What is a synaptic operation? Different definitions for all the chips. What are the contributions that are included? Is it only the neuron, only the synapse? Does it include the connectivity? Actually, if you look up the preprint history of Odin, you will realize that my definition of the picojoules per synaptic operation has changed over the multiple versions of the Odin paper because as a PhD student trying to make things fair, I realized that there was a bit of a gap on trying to make things consistent. And so this was a big part of this proceedings of the IEEE paper. It was also a struggle that slowly led to this benchmarking effort. And I have to say a big thanks to reviewer 2 of the Odin paper, who ended up being the nasty person who pointed out that I was taking shortcuts. I think a lot of this effort in making things fair is coming out from the comments of this reviewer.
Okay, so we'll get back to Neurobench a little bit later, but I think no one can say that your 2023 paper had any shortcuts in it. It was so comprehensive and so detailed in terms of trying to cover every different approach and put them into context with each other. So you wrote it with Giacomo Indiveri and with David Ball, who I actually don't know, so maybe you could tell me a little bit about him. How did that paper happen?
So it's really coming from my PhD work, and David Ball is actually my PhD supervisor. David is an amazing hardware designer, and this neuromorphic engineering thing that I started during my PhD was a joint venture because, it was new for both of us. But David also has the sharp eye in asking the right questions, and that definitely shaped this goal of making things fair. And so first going bottom up with Odin and MorphIC, then going top down with Spoon, I had these 3 chips and I figured out, okay, that's perhaps the natural way of structuring my PhD thesis. And then I went to the lab of Giacomo Indiveri on my postdoc, and things were matured at that time with the last chip, Reckon, and that really made the best of bottom up and top down. And that was the time to basically bring this journey together in this proceedings of the IEEE paper.
Okay, so why don't you say just briefly something about Reckon? Because although we have had a podcast with Giacomo, some people won't have heard it. Now, Giacomo famously takes a very kind of analog, subthreshold, sort of old school neuromorphic approach to building his chips. So maybe you could just say something about that, because one of the other things that impressed me about this 30-page paper was that it was the 3 of you, obviously you coming from a completely digital background and he coming from that analog neuromorphic background.
Yeah, so the Reckon chip, I would say, is a purely digital design with a really neuroscience-inspired approach. Reckon is an on-device learning chip whose goal was to bridge fine-grained temporal dynamics over milliseconds to behavioral timescales over seconds. So the goal was really to learn over timescales that can span orders of magnitude. And the issue with that is that if you use the workhorse of deep learning, which is backup through time, then the problem is that you need typically a lot of external memory because you need to remember all the state of the network over the dynamics. And the key insight was eligibility traces, which are computed online in a forward-in-time fashion. And so you can really apply your updates in real time. And so this was completely getting rid of the need for external memory. And therefore, you ended up with a chip that was very efficient because this external memory just wasn't there. And you could fit on-device learning over keyword spotting, gesture recognition, with real-time online learning over 50 microwatts. So this is really an enabler for adapting to patients' healthcare in wearables. So the whole idea of taking eligibility traces, so these low-pass filtered long traces that you could actually implement perfectly in an analog fashion with slowly decaying capacitors. It was just implemented in a digital way as a proof of concept to iterate quickly on the first iteration. But I believe that the Reckon chip actually would go a long way in a V2 by keeping, for example, all these synaptic array in a digital fashion for scalability, and keeping the neurons and the traces in an analog fashion so that you can really cut the data movement between memory and processing by just keeping this tray slowly decaying before you fetching from a memory, computing what is the decay and storing it back. So that's definitely the main bottleneck of Reckon today. So if I were to do it tomorrow properly, I would move it mixed-signal.
So talk more about the paper and the process of writing this paper. How much was from your thesis and how much was added to later in terms of your collaboration with Giacomo?
So the Reckon chip is really making the best of this bottom-up and top-down approaches. So what I figured out during my thesis is that if you start from a purely bottom-up approach, it's just so difficult to make it work. So what you actually need to do is to start from a more top-down approach that may not be bio-inspired and to bring in insight from neuroscience. So what the Reckon chip did, you start from backprop through time, and really the nasty non-neuromorphic way of doing things. And you then look up into neuroscience and figure out that eligibility traces are needed, which is exactly the contribution that was done in EPROP. So that's not us. But then what we looked for is that EPROP per se, if you do not have the right ingredients, which means neurons learning with very slow time constants, such as threshold adaptation, it cannot learn over long time scales. So if you just take a plain leaky integrated fire neuron, it won't learn these tasks over behavioral timescales. So what was proposed in the EPROP paper was to use adaptive leaky integrated fire neuron with this slow threshold adaptation. The issue, though, is that if you implement that on hardware, the EPROP equations for the ALIF neuron are just a nightmare. This is just way too expensive. So this is where we stop having our neuroscience hat. We take on, again, our engineering hat, and we figure out another solution to solve this problem, which is to take back the standard leaky integrated fire neuron, but to have a memory potential time constant that can range over hundreds of milliseconds or seconds. This is not bioplausible, but this solves the problem in a much simpler way, even in the sense that you can store the eligibility traces per neurons instead of per synapse. So this scales much better. This is much easier to implement. And you see that we have gone on this journey from engineering with backprop through time to neuroscience with eligibility traces and adaptive leaky integrated fire neurons, and going back to engineering to finally making things efficient on the chip. And I think that's where we really reach the best of what is done in Giacomo's lab to really take on this bio-inspired approach. And basically, I took on back my engineering hat, digital designer, to really plug everything in a very efficient digital chip. But again, the next step would be to go mixed signal for this one.
One of the things that I've noticed about you, Charlotte, is that you've made a huge impact in a very short amount of time. If you consider that your very first chip broke records for the amount of power used for synaptic operation. And I get the impression, both from reading that paper and the other papers that we've talked about, that you're very focused in the way you work. And I wonder if that's what you put your success down to, going down the rabbit hole of all of the different approaches in neuromorphic and then really trying to think clearly about the choices that you want to make in your work. And the reason I'm asking you this is I'm wondering if you have advice for people who are in their second or third year of a PhD right now, which is always the worst time. I always think the second year, which is where you're flailing around, figuring out where you're going to make your mark.
I actually believe that most of the impact of my chips comes from the fact that they're simple. And the good thing is that optimizing for simplicity and efficiency is oftentimes the same thing. So the core advice I have in making things efficient is optimize for space and time locality. If you make your algorithms local in space and time, that can take many different forms. We have talked about it for learning with Reckon, for processing with graph neural networks. This is always about locality in space and time. And if you simplify to the point that you make things local in space and time and you maintain performance, so that's easier if you start top down, then you end up with a very simple design that is going to be very efficient. And then if you open source this is going to have a very big impact, because I believe that the hardware field is currently missing a lot on having open source works. So if you look up machine learning, I would say one paper out of two, if not more, has an open source GitHub repository. And this is what allows people to build on top of each other's work. In hardware, this is very difficult to find open platforms. So you have some in terms of microcontrollers with famous groups, such as the Pulp team and so on. But in terms of neuromorphic engineering, Odin was the first chip to be open source. And so I really believe that be selfish, open source your work and maximize your impact. So just make things simple, local in space and time, and share your work. And I think this is going to be already a big step in maximizing the impact that you have. And another one, stay curious, because just being curious about what's out there, giving it a try, see if things can be combined beyond staying in a given school of thought. Yeah, I would say this is definitely the way to stay on top of the field, stay up to date and have impact.
But going back to this review paper, right, what interested me was that you did a really proper job of mapping the landscape of neuromorphic engineering in that paper, going carefully through all of the different design choices that people can make. And I have not seen that done before. I've been looking at neuromorphic papers on and off for 30 years and haven't seen someone really categorize them all and name them all and put them in quite such a clear review. And I wanted to know your motivation for doing that. Was that just what you felt you had to do for your PhD, or was that more preparation for Neurobench, that you had to understand the whole field to start the Neurobench ball rolling?
So I really think the rationale behind this paper was, what do I wish I had known starting as a PhD student in that field? So all these trade-offs, I realized looking back that I just had no clue about them. So I would say that Odin was a lucky incident in the sense that I just wanted to do things efficiently in digital, and that my understanding of all the trade-offs involved has changed so much over this journey. And I hadn't seen a paper covering this, so I thought, okay, why not give it a try?
And 330 some references later, I'm just in awe. I'm writing a book at the moment, so I know how difficult it is to do something of this scope. How long did it take you?
Since this was started with writing my PhD thesis, it really started at that time. So I wrote my PhD thesis end of 2019. This was the background of that paper. And then it got tremendously refined over my postdoc, because it is there also with the experience of Reckon, I got some insight on how to merge these different design choices. I just refined it a lot. And when you refine stuff, I guess the reference list grows naturally. But yeah, this journey is from the writing of my PhD thesis in 2019 until the publication in 2023, including the reviewer iterations.
So a long journey. What insights came out for you? You know, having done all that refinement, having cataloged all of these different areas of neuromorphic engineering, what were the things that you found most surprising, the most useful, the most counterintuitive?
Oh, that's a very tough question. I would definitely say that what struck me, and that also was at the beginning of my PhD, is there are so many approaches in this field. And this is both a strength and sometimes a curse as well. I think this field has tremendous opportunities going across the approaches instead of just picking one and sticking to it. And having this overview of all the approaches, trade-offs, design choices is a step in encouraging exploring the frontiers of all of those. And going into that benchmarking aspect that we have mentioned quite a few times, I think this is also what was hindering the development of previous benchmarks before, that there are so many design schools, it's almost impossible to formalize benchmarks where all of them can shine. It's impossible. So I strongly believe that any development in the field of neuromorphic engineering needs to be imperfect. You can only embrace, I would say, 2/3 of the approaches, best case. And the only thing that you can do is to expand this effort over time. So if you want to get the ball rolling on anything, you have to do your best guess in covering many of the approaches, but have to do the extra push in having this long-term maintenance where you can add stuff over time to make sure that you can encapsulate and improve the coverage of all the approaches. And I think this is what was really key in making Neurobench happen. We brought the community together asking, where do you think the gaps are? We got a pretty good list, also with people willing to dedicate time in making this happen. And then we realized, okay, we cannot do all of them. Our goal is to agree on a first iteration that maximizes the interest that there is currently for a first iteration, and to keep it really evolvable over time to add more benchmarks as new approaches pop up, as extra approaches can be accommodated for, as people have time to contribute more, also depending on ongoing projects. And so to zoom back to your initial question, I really believe that's the case. We have to make sure to embrace this diversity of approaches, but embrace it in such a way that is actionable, and to not let stand in our way of not doing things because they are not offering a perfect coverage. I think to go forward, this is really what is needed.
So of the new benchmarks, can you talk about, say, one in particular and why you think it will be an important contribution to showing what neuromorphic engineering potentially has to offer?
So these benchmarks were really designed having in mind, okay, what are tasks where neuromorphic engineering can shine? And so these are not specifically tailored to neuromorphic approaches. All approaches are welcome, and this is really for ensuring fair comparisons, because it's a really critical thing now to demonstrate a competitive advantage compared to conventional approaches. But so we came up with actually a wide set of benchmarks. So we have an algorithmic track and a systems track, because again, different design schools focus on algorithms, some focus on systems, and we have to make sure that all of them can have some ground truth to compare to. So on the algorithmic track, we have currently 4 new benchmarks, and I will pick one of them just because it has created quite a lot of enthusiasm at the moment, but I definitely don't want to pick this one being the only one useful. It's really community driven, and all of them are really important to the field. For example, on-device learning is one of them. But I'm going to focus on the primate target reaching task. So these are brain recording from primates who have to reach a target. And from these recordings, we have to infer what are the movements that the primate is doing. And why do I want to talk about this one is because out of it, we made a grand challenge in the BioCast conference in October. And there were many submissions. It really brought in new insight. There was a paper on all the tips and tricks that are necessary to train spiking neural networks. There were papers on novel approaches. And so all of those bring new contributions to the field. And we see that this is an effort that is going on. There was so much enthusiasm that now we want to make it happen again as a grand challenge in BioCast 2025. But with a slightly more complex twist. I'm saying this for the auditors who might be interested in giving it a try. It's coming again at BioCast 2025, most likely with closed-loop experiments this time. This is really where I think such benchmarking initiatives can shine, is just getting the community together, excited on solving a challenge. And then, the outcomes were just much broader than what we expected.
Now, your latest work involves using event-based graphs for low-power, low-latency vision processing. Can you talk about that work?
So there's a long-standing question in this field as, should we use spikes? This is a very controversial question that I wouldn't even dare to tackle in a podcast. But the safer way to ask the question is, where are we certain that spikes can be useful? Or more precisely, where are we certain that event-based computation can be useful? And when you have a stream of events, data generated by these event cameras is typically very sparse. And so this event stream can be seen as events in space and time. And a very efficient way to process sparse streams of data is to represent it as a graph. And so every single pixel that spikes in an event camera just generates a new event in your graph that is connected to previous events, and therefore previous spikes from pixels that are nearby. And nearby can have many definitions, and nearby here means within some spatial temporal distance of former events. And so we therefore had a look into graph neural networks, because if graphs are a good representation and graph neural networks are good at processing graphs, perhaps there's a way to make something. But the issue is that current approaches rely on static graphs. So what that would mean is that you need to wait for your full graph to be generated, and then you can process it. But this is really not what we want to do if we want to reach very low latencies. We just want to pick a new event, update the graph, and then update our prediction. So a static graph, which is a standard approach, is really not the way to go. But there was luckily really recent work by the group of Davide Scaramuzza in Zurich, who was looking into asynchronous graphs. So here the word asynchronous just means that you receive a new event, you update the graph locally, and that's the key word there, locally, you update the graph, and then from it you can update your prediction. And so what a graph neural network is doing is just exchanging messages between nodes. So you really see that the whole idea of neuromorphic computing, which is processing things in an event-based fashion, keeping computation local so that you save on your data movement and on the von Neumann bottleneck, graph neural networks are really about those two core ideas. And so we wanted to accelerate those event-based graph neural networks in hardware. We figured out a few nice ways to actually benefit from some parallelism in the hardware to accelerate that efficiently, to compute very easily once you get a new node. How do you figure out where are the neighbors without completely fetching the whole memory of the past? So basically, this is the rationale that we took. And the hardware itself is quite simple. And nevertheless, for a real-world dataset like NCARs, which consists in classifying background images from car images, but generated from event-based data snapshots, we can reduce the latency per event to 16 microseconds. So this is really fast and close to the temporal resolution of event-based cameras themselves. And we are not aware of previous work achieving such low latencies on real-world datasets such as NCARs. So we are just super excited about these event graph neural networks, and now we are looking and developing custom hardware for it that would allow it to scale to HD images.
So tell me about what the hardware would look like that would optimize the processing of these graph networks. How would it be different than any other kind of neural network hardware?
So here, the magic in processing graphs efficiently is about storing a good representation of your graph. So what we did in this latest paper with an FPGA implementation was for every single pixel, we keep a queue of events, of the last bunch of events. And so that way, once you receive a new event, it's very easy to just look up the nearby queues representing the nearby pixels and see if there are recent events. And so you see, this is how you identify neighbors in both space and time. So that's the easy hardware. But if you imagine that now you scale to very high resolutions, this storage scales with the number of pixels. And so the way to make it scalable is now you have to come up with some fancy cache strategies to make sure that you do not need to store all the events on the chip. You will need some external memory, but you are hiding the cost of that memory by just reusing whatever recent events you have recently accessed that might still be in your cache. And so that's where the magic happens. So it's not really neuromorphic in the sense that you don't have an array of spiking neurons and synapses, but this is still about solving the von Neumann bottleneck and accessing local information efficiently.
So one of the other issues you raised in your previous paper was about convergence of digital and analog approaches. And I wondered if you wanted to talk more about that. Do you feel that analog has a place other than as a research platform?
Oh, I definitely think so. Even if you look up the standard machine learning accelerators, no neuromorphic at all. You do have accelerators that have some computational primitives that are implemented very efficiently in the analog domain. Same for analog in-memory computing. I would say this is in the realm of standard machine learning accelerators. Based on SRAM, you have this analog in-memory computing. But this is very much neuromorphic, I would say. This is analog. This is about bringing memory very close or inside compute. So the short answer is yes, analog is really out there for efficiency. I would say where digital is out there is for very quickly iterating on the co-design and generating your first proof of concepts. Things are just much, much faster and reliable in digital. And so where both meet is at the second iteration. So you first do the co-design in your first iteration in the digital domain, and then you should bring it in the analog domain. And how to make the best of both worlds is to, now that you have specifications and that you have made your first iteration very efficient and you have identified the bottleneck, you can identify precisely what needs to be moved in the analog domain to get a competitive advantage. So this is really about deriving, okay, what are your specifications for every computational primitive? Do we keep it digital for reliability and high precision? Or can we move it to the analog domain because we don't need much precision? Having noise might even be beneficial. And this is really on a case-by-case basis. For every co-design case, the answer will be different. So this is why you first iterate quickly in digital, and then you make things much more efficient in analog.
Can you talk a little bit about the experience you've had with on-chip learning, in-memory computing? Because I know that's something that you're interested in.
Yeah, I'm just super excited about on-device learning. I think this is one of the areas where neuromorphic computing can shine. And that's no mystery that one of these benchmarks in Neurobench is focusing on specifically this question. I think Reckon was a super nice first iteration in bridging these many different time constants. But actually, it has two very big issues. First, it's not scalable in the sense that this only one layer, and EPROM doesn't scale to multiple layers. So you need extra developments there. And the second aspect of it is that it's really not data efficient. If you want to learn at the edge, you cannot ask your user to repeat a word 1,000 times until it converges. This is just not possible. And yet this is the assumption that Reckon is taking. So the future of on-device learning is really about few-shot learning from very little data, continual learning. So learning with new data on the fly whose distribution might not match or might deviate from the one that was used during training. And this is something that we are really actively working on right now, how to keep the learning mechanism as simple as possible. And one of my key points there is that learning should be seen as much as possible as a plug-in to inference, because we know how to make processing devices efficient. So if you can build on top of that, you can make your learning really efficient as well. So this is one of the ongoing research tracks in my team. There's a chip that is back from fabrication and working, and I just can't wait to share it as soon as the measurements are finished. And the second part of your question was also about in-memory computing. In-memory computing is really about not only efficiency, but also latency. And so we mentioned this graph neural networks for low latency processing. In-memory computing really has a role to play there on both the efficiency and the latency sides. And the idea that we are working on at the moment is that you have two types of in-memory computing. You have analog in-memory computing and digital in-memory computing. And digital in-memory computing actually fits super well an event-driven processing scheme. So I really believe that digital in-memory computing is the way to go for event-based packing neural network execution. And we can demonstrate that indeed the latency can be reduced a lot. But then you have a key problem. You cannot overshoot on the efficiency of your digital in-memory computing macro. Because if you make it like extremely efficient, and we see papers published with peta operations per watt, like insanely good numbers, but these papers ignore the fact that this in-memory computing macro is inside a bigger system. And if it's not flexible, you will spend your time shuffling data from the external memory to the in-memory computing macro. So system-wise, these nicely optimized macros are just terribly inefficient. So the way to make your system much more efficient is to actually bring in flexibility. And this digital in-memory computing macro with flexibility for spiking neural networks is a chip that we have recently published at Discuss. So this is also a hot off the press stuff that I'm really enthusiastic about.
The last question I wanted to ask you was about what in the field inspires you, things that you're seeing other people doing that you think are going to make an impact in the long run.
Thinking about it, actually, I believe that most of the papers I read for now are not hardware papers. They are either on the neuroscience side or the machine learning side. And this is really the wonders about co-design, is that this is an open playing field, especially if you are about to merge insight from neuroscience, machine learning. There's so much to do. And every time I see a new paper coming up with a very novel idea on these sides, I just can't wait to try it out. Exploring this co-design landscape might turn out to be a dead end. But if not, you're almost sure that this hasn't been attempted before. This is just an open playing field waiting for you when you see a new nice idea on the sides of neuroscience and machine learning.
Can you give an example of, say, a neuroscience paper you've seen recently that's made you think, ooh, I want to get my hands dirty with that one?
I'm a big fan of cortical microcolumns, anything linked to the neocortex. I'm not the only one, definitely. This is just the thing that the brain has come up with that is naturally scalable while being very shallow. So in that sense, it's completely different from deep learning. And whenever I see a paper that is, okay, here is some new insight on cortical microcircuits, I'm just super excited about it. And also now you have these powerful recordings that can record many, many neurons in parallel. And that, I think that's just such an amazing opportunity to figure out what's going on, because we just didn't have this data before. So there was this famous paper, Cortical Mini-Columns, a structure without a function. This is still completely open research questions, and having the opportunity to give it a try with new data and new insight and explore this co-design landscape is one of the things I'm the most enthusiastic about.
Charlotte Frenkel, thank you for coming on to Brains and Machines.
Thanks so much for having me.
Thanks, Sunny. I really loved the sincerity with which she talked about the pain and the journey to obtain meaningful results. It was honest and a pleasure to hear her story. And for more about Charlotte Frenkel's work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Ralph Etienne-Cummings from Johns Hopkins University.
Hi, guys. Happy to be back. Happy to talk about this great piece of work, by the way.
So, yes, great episode. And one of the first things that I want to mention is that she says that there are so many approaches to this field, and I agree. And this reflects on the difficulty of defining consistent and meaningful benchmarks metrics. So how can we really approach standards for this community for benchmarking digital, mixed signal, and analog? And then what are the risks on underdefined or inconsistent benchmarking metrics?
So this is a very fraught subject, right? And there are folks that have quite different perspectives on even the need for benchmarking in this domain, like Brad Amoni at Sandia, who truly believes that benchmarking will stifle innovation because it forces everyone to kind of conform to a particular set of metrics, and it doesn't allow us to be creative, right? Creativity is exactly the notion of being out of the box. But if you are confined to the box of the benchmarks that's been defined for the fields, then nothing new, nothing innovative will happen. What happened in the speech domain, right? Which is at 0.01% improvement every cycle in order to get it a little bit better. Now, granted, if you look at speech recognition today, it's amazing, right? But it happened leaps and bounds. There was a point where everything just jumped, right? So I want to be careful that we don't get too locked in this notion of having to have specific benchmarks. What I liked about what she said was, look, benchmarking is difficult. We are not going to have any one set of beautiful, really confined and always used set. It's going to be a dynamic, evolving thing. It's going to have some good parts, some maybe not as good as others would like, and so on and so forth, right? So that flow of dynamicity around even the measurements, the metrics, I think is important for creativity, innovation, and going forward.
So I'd like to say that as someone who looks in from the outside, one of the things I'd really like is just for people to be really clear about why they're using particular units for things, right? So for me, it's less about the task and more about the way you express numbers. So for instance, some people express in synapse operations per picojoule, and some are discussing in max. And when you're looking in from the outside, you're trying to do a review as a scientist or trying to write an article as a journalist, as I would do, it's really difficult to know whether you're comparing apples and oranges, because all of the assumptions, what goes into that number, even if you are using joules or whatever as your unit and you all agree on what kind of computations per unit, you don't always know what's included. So is the off-chip communication included in these numbers? Is this a global systems number, or is this just the stuff that's being done on the chip or even in a very small part of the chip? In terms of basic science, just the units that we're all using, the assumptions we're making in doing these calculations, I think it's not always transparent. And if we could even just do that as a community, I think it would be a big step forward.
This part of it, I agree with, right? In the sense that it's the units. Those are fundamental, right? And also writing good papers means explaining what you mean by your measurements, right? So those kinds of things I think are different than the benchmark question. The benchmark question is more about MNIST. We wanted to get to 95%. That's the benchmark that everybody who's doing spike-based learning should be, striving to compare themselves against. Those are the things that I think kind of can be a little bit more confining and maybe less innovation inspiring.
I agree with that, but if we can't even get that basic thing right of the metrics and explaining all of the assumptions and making those crystal clear, then how is it going to help us to have these benchmarks? And there have been some discussions, I don't know quite where it's moved on to since NICE, where Jason Yip came on and talked about where we've got to with Neurobench. But there's a lot of dissatisfaction with the fact that there are no real dynamic systems approaches to things that are within the Neurobench framework yet. Now, of course, if Jason were sitting here, I'm sure he would say, well, that's up to the community to come up with, what should these tasks be? And then we can include them in the framework, and all they have to do is this, this, and this. And I'm sure that's true. But I think that's an important step, is to make sure that the tasks that we're setting for Neurobench are ones that Neuromorphic really wants to be solving.
I just wanted to comment that the community is us. So it's him as well, right? So we need to come out rather than with tasks. For example, one of the things that I'm doing with Elisa Donati is coming out with ingredients to get out some figures of merit, right? So instead of being stuck on specific task, is, okay, I give you the ingredients. So whatever task you come up with, which would be, depending on the environment changes, depending on the difficulty and so on and so forth, you need to come out with metrics with which you can create your figures of merit. And then we can compare and benchmark. So this is one of the projects that I am carrying on with Elisa, for example.
So here's a question I have, right? I remember reading different magazines on the latest microprocessors. These were in the days of the 486s and whatnot. And there was always the benchmark little bar graph at the back saying, this version of the microprocessor got it this far and the other one got it that far, but this one got only this far on this particular benchmark and so on. So the question for me that kind of going through my head is, when did that start happening? I think it started happening when the architectures started to look extremely similar, because it was not really pushing anything new and innovative and creative anymore, right? It was just now I'm just going to try to squeeze every last bit of performance out of this known architecture. Yes. But Neuromorphics was so far from those standardization that I think it becomes, while useful amongst us, so to speak, to say, hey, I've moved this thing forward a little bit, but I don't know that it's useful from a grand scheme of things.
Okay, so I'd like to go on with another comment. So I often see people studying analog chips and then for practicality going to digital. She goes the other way around, and I found it amazing. But apart from that, she talked about eligibility traces, right, which is a temporary record of the recent visit history of state actions pairs. So how does that compare to backprop, and how this can provide a scalable foundation for future learning capable neuromorphic processors? And then the question is always, what is happening in the brain? Do we have this system of eligibility traces, or what I think is much more complex than that? Because we just don't look at the near past, but we have much more information there.
Yeah, so at the end of the day, I believe the question is this notion of credit assignment, right? So you've got a flow of information through the network. Certain things affect the synapse of a particular neuron in a certain way, where others don't, right? And it's a question of, if you want to make architectures that are efficient, you only want to update and pass the interactions forward that actually have an impact on the synapses, right? So that gives you kind of a stripped down, sparsified flow of information through the network. So in that sense, you could argue that maybe the eligibility trace tries to capture that from not a backprop perspective, but something that's analogous to the credit assignment question in backprop. Now, the idea of continuous online credit assignment or a development of that kind of mechanism for updating specific synapses and so on, it's something that's down in the weeds of what's going on inside of each network, but I don't know whether I see it as a reflection of what may be going on in cortex, right? In the brain. And it seems to me to be so different in its very nature of construct, right? Where one is such a mathematical / engineering mechanism for distributing credit, whereas I don't think that that's how it's happening in the brain. And honestly, I don't know how it's actually happening in the brain.
Okay, so one of the things that she said the good thing is that optimizing for simplicity and efficiency is oftentimes the same thing. And I loved it, and I can't say how much I agree. Then she talks a lot about graph neural networks, and I should read more about this because it's really intriguing and interesting. My question would be, how do you envision the other implications in the future following this graph neural network architectures?
I think there as well is another thing that we can learn from other fields, right? So in speech, that has been one of the big ways that, massive innovations has been made in terms of looking at the history of particular word utterances and how that then predicts what the next set of words would be, and therefore understanding what the speech is, right? So in a way, it's almost along the same way, except now we're dealing again with single neurons or group of neurons that comes from a part of an image or something to that effect. So I think there's a lot to be said there, a lot to be explored, and it might be the thing that makes event-based processing, kind of more compact and more predictive. So essentially predicting the next byte in the network, that might be the equivalent of that, and then ultimately then looking at the ensemble to try to figure out what does it mean. Then you're looking at the full graph, right, to try to say, oh, that shape means a blue car was about to hit a person or whatever the thing happens to be, right? So it's interesting, and I don't know enough about it in terms to be able to say more than high-level observation of what's going on. But she said that she has a chip that's already in her lab measurements, so I'm really curious to see what it does and what are the problems that they're trying to attack with it.
Definitely. Another thing that I would be curious, and I think we talked already about this with Simeon Bamford episode, about the rewiring, because once you get the network done, the architecture is done, how do you rewire then to attach your connection to different synapses or different nodes? That would be actually super interesting, right? Because specifically in the neuromorphic community, every time you need to come out with a structure that is static, you have that structure, and most of the time it's your gift and a curse, right? Because you cannot move it from there, but then you're fast because you're taking insight because of the lateral connections that you created. But it would be cool to see how to rewire and to create the network on itself. It would be nice to build networks on their own, also from the structure point of view.
And it sounds like also it's like a changing of the projection fields, right? So who does each neuron speak to? And who should it speak to? And that might be a function of the information that's flowing through. I don't want to say task, because task implies kind of a high-level thing, but at least what the information flow is, right? So neuron 1 may speak to neuron 5 in terms of the transfer of information for a particular situation, but it may speak to something else in a different situation. So how does one update that graph now, right? To say, hey, you went from here to here, now it goes from there to there. And what does that mean? Well, that means that Ralph was eating a banana versus eating an apple. That kind of correlation is interesting, and I don't know whether it's the kind of direction that she's going with her chip, but it would be interesting to see what others, what's the prediction of where it should go based on what the data that's come through. I guess the curse of age, is that you always have seen other things in the past, and we always kind of look back and say, oh, I've seen this before, or this happened then, or something like that, right? So, Sunny, you were so laudatory of the comprehensiveness, if you will, of the paper that she had written on the top-down and bottom-up design of neuromorphic systems. While I am also quite laudatory at the fact that it is quite an extensive study and so on, I do think that there are some important pieces along the way that were missed. For example, the Goldberg paper on IFAT. I think you cannot speak about spike-based processing without speaking about that one first, and that is early 2000s, right? And then you go far enough back, you get into early 1990s, where you start looking at the Corticon chips that came out of University of Pennsylvania, or even on the digital side, what Dan Hammerstrom did with adaptive solutions, right? So there's, anyway, all that's to say that while this piece of work, obviously 30 pages of it, there's only limited amount of information that you can actually put in within 30 pages, right? The beauty of the book that we're writing, Sunny, is that it allows us to go a little bit back further, and we can therefore capture some of those, maybe those missing pieces.
But we will add some of your references, Ralph, to the webpage, so that people who want to look up Dan Hammerstrom and the IFAT paper will have a place to start. I just want to point out to listeners that we're talking about the bottom-up and top-down paper.
Yeah. Second thing I noticed as well, like her figure 5, she gives these 3 breakdown of different ways that spikes can be communicated, right? It's either spike rate, and then the other one is spike rank, and then the other one is spike time. I really like spike time, right? Because the information is actually encoded in the time between spikes. That length is really what the data that's been communicated. The events themselves, or the spikes themselves, are only telling you about when to start kind of paying attention, so to speak. Anyway, that's one of my area of interest is interspike intervals.
Okay, well, let me make 2 comments then. I'll start with that paper. So what I really appreciated about it is, having read loads and loads of papers in the field, one of the things that I really wanted was someone to talk me through why someone made that design decision. And some of that was in there. Not all of it in 30 pages and 300 and something references anyway. There's no way you can get to it all, but I appreciated that. I thought it was much more systematic than a lot of other papers I've seen, similar reviews, and the fact that she had a lot of space probably helped with that. The only other thing I wanted to say was that, having spoken to Charlotte before, I was pleasantly surprised, because knowing that she's a digital designer, I first met her sort of during the tail end of COVID. I think it was 2022 when I went to my first Capocaccia. And on the way back, I visited a whole bunch of labs. And I was kind of worried that there was going to be a real analog digital tension. And what I really liked was her approach to it. And in fact, she changed my introduction to the podcast. She added a few little words, which I thought was really illuminating. So she said that digital approaches are not the sort of core of neuromorphic engineering. They're a way of prototyping neuromorphic engineering. She used the term proof of concept, but whether you then implement that as either analog or digital is then left to the reader's imagination, which I actually thought was a really nice, open-minded way of looking at it for where we are at this point in technological history. So I feel like I've learned a lot from having studied her papers, although I think I'm going to have to read that 30-page paper again. And the first time, I think it took me 4 or 5 hours, because I was reading it carefully and making sure I understood things that, maybe I hadn't understood before. And I have to find that time again.
And look, there's a plot that she has, figure 6, I think, in the paper, exactly speaks to that point, Sunny, which is she's got different examples of implementations, right? And some of those things were done in FPGAs, purely digital. But they were trying to capture, let's say, the 20 faces of the neurons that Izikevich talks about, right? And then ultimately, folks went and implemented those features exactly in circuits that would then capture as many of those faces of the neurons as possible. So we've seen that juxtaposition and that development along the way. And a lot of grants that I've been involved with and a lot of proposals that I've seen tends to take that route. You first prototype it in digital, you prove the idea, and then you think about how to do it in mixed signal or pure analog as appropriate.
Okay, guys, let's stop it here for today. Thank you, Sunny, for yet another great interview, and Ralph for your insightful comments as usual. In the next episode, Sunny will talk about robotics to Gordon Chen, professor at the Technical University of Munich at School of Computation, Information and Technology. We hope you will join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks again to our guest, Dr. Charlotte Frenkel. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find the transcript, along with direct links to the other stories we've mentioned and other resources. Thanks for listening.